Bismillahirrahmanirrahim. In today's lecture of the course of thermodynamics, we will discuss the several topics. Some of the topics are the specific heat of water, how we can calculate the specific heat of water. The other is the first law of thermodynamics for hydrostatic systems, and at the end we will discuss quasi-static heat flow. That will be actually the heat reservoir. The first objective is to understand the specific heat of water and to understand the definition of calorie. The most important thing is why we use a very interesting definition for calorie, that is actually the amount of energy needed to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees centigrade. And the second part will be devoted to the development of first law of thermodynamics for hydrostatic systems. That means the first law will be modified and some of the dependent and independent variable will be the differential of that variable will be calculated, and new form for the particular hydrostatic systems will be developed. And at the end we will discuss the quasi-static heat flow between a system and surrounding, and also need to know the explanation of heat reservoir. So what are we need to know what are the actual conditions for the heat reservoir of a particular systems. So the first thing we need to know in this lecture is the specific heat of water. If we go through the history, in the middle of 18th century, the measurement were between the freezing point of water and the boiling point of water. Just like we can see, that were actually the relative measurement between freezing point of water, that was considered as a 0 degree centigrade, and the boiling point of water was considered as 100 degrees centigrade. So the calorie was defined as the amount of heat required to raise the temperature of 1 gram of water through 1 degree C. At that time it was assumed that calorie is actually the amount of heat that is required to raise the temperature of 1 gram of water through 1 degree C. But later on, when several experiments or a series of experiments were performed, then it was found that the amount of heat required to raise the temperature of 1 gram of water from 0 degree C to 1 degree C is different to that of from 30 degree C to 31 degree C. It means that the amount of heat or energy needed to raise the temperature of water of 1 gram at different degree C in some cases are different from each other. Later on we will see in the curve how it's different from each other, but generally in this case we can say that the amount of heat required to raise the temperature of 1 gram of water from 0 to 1 degree C is different from the amount of heat required to raise the temperature of the same 1 gram of water from 30 to 31 degrees C. So then calorie was defined as that is the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees C to 15.5 degrees C. That was actually the simple definition that is even applicable till now. That is actually the amount of heat needed to raise the temperature of water from 14.5 degrees C to 15.5 degrees C. So actually when the water temperature is increasing, what happens? The amount of heat dissipated by water either by maintaining a current in a resistor that is immersed in water, or in other case by churning the water in irregular manner per unit mass of water from 14.5 to 15 degree C was actually called as the mechanical equivalent of heat. It was called as the mechanical equivalent of heat, and its magnitude was equal to 4.160 joule per calorie. So this mechanical equivalent of heat is actually the calorie. So this mechanical equivalent of heat was actually also called as the specific heat of water. But that time the specific heat concept was not so much developed, so that is why it was called as a mechanical equivalent of heat. So later on it was given as the specific heat of water. So what is the specific heat of water at constant atmospheric pressure? If we keep the pressure constant, so how how the specific heat of water changes with different degrees of temperatures. I mean, here we can see the amount of heat required to raise the temperature of 1 gram of water at different degrees C. Here we can see initially from 0 to 10, from 0 to maybe 1 to like this, it's high, so gradually there is decrease in it, and at around 30 to 40 there is very small variation. Almost is not very constant but almost constant, and further beyond 40 there is gradual increase in the magnitude needed to the magnitude of heat needed to raise the temperature of 1 gram of water through 1 degree C. So here at 100 degrees centigrade, the amount of heat needed to raise the temperature to 1 degree C, from 99 to 100, that is almost equal to its amount of heat needed to raise the temperature of the same 1 gram of water from 0 to 1 degree C. So this is something what we discussed in the earlier slide, that there is variation between the heat when we go through it, and that variation is due to the heat capacity, or that is due actually that is different from each other. So that is why it was considered specifically that calorie is equal to the amount of heat that is required to raise the temperature of 1 gram of water through 14.5 to 15.5 degrees C. So here we want to develop the equation for a hydrostatic systems, and that is actually the modified equation of the first law of thermodynamics. We need to modify the simple equation of first law of thermodynamics for a special case, that is a hydrostatic systems and water is closed in a cylinder. So we generally know that the mathematical formulation for the first law of thermodynamics is very simple, where dq, that is the amount of heat provided to the system, is equal to the sum of change in the internal energy of the system plus work dW. But here in this specific case we need to modify the dW into pdV. P is actually the pressure and d is the change in the volume. So the modified equation of first law for the hydrostatic system is equal to dq is equal to du plus pdV. We have replaced dW by pdV. So here the U, that is actually the internal energy, that is a function of 3 thermodynamic coordinate, that is the pressure, volume and temperature. So in these 3 thermodynamic coordinate, 2 are independent coordinate while the third one is dependent coordinate. So if we consider in this case for the T, that is actually for the T and V, so what happened, this equation could be written as a du is equal to change in internal energy with respect to T when the volume is constant, and similarly change in the internal energy with respect to volume when the temperature is constant. This is the simple equation of du. So what we need to do, we need to put this value of du in the above equation, that is dq is equal to du plus pdv. So this equation will be modified like that dq is equal to change in internal energy with respect to temperature when volume is constant plus into dt, and change in internal energy with respect to volume when temperature is constant plus p whole into dv. So what happened, we have just rearranged the same equation and we divided both sides of the equation with dt. So what happened, we can get the equation that is equal to dq divided by dt, that is actually equal to change in internal energy with respect to temperature when volume is constant plus change in the change in the internal energy with respect to volume when with respect to temperature. Now with respect to volume when temperature is constant plus p into dv divided by dt. So this is a modified equation. We have just divided both sides by dt. So what happened, dq by dt is actually the amount of it. So here we can see the simple things that change in dq divided by dt at constant volume is equal to change in internal energy with respect to time when with respect to temperature, when volume is constant. So this is for particular case when the volume is constant. So what happened, we need to put that equation. If we see the left side of this equation, here in this equation, when we keep the volume constant, so what happened, this change in volume will become equal to 0. For the case when the for a constant volume, what happen when we consider constant volume, so this change in volume will be equal to 0. So this whole term will become equal to 0. This whole term will become equal to 0, and we will have only this term. So for constant volume, dq divided by dt into constant volume will be equal to change in internal energy with respect to T, with respect to temperature when volume is constant. So the whole term vanishes because this term become equal to 0, and multiplying something by 0 will make it 0. So we can get only these things, dq divided by dt with when the volume is constant is equal to change in internal energy with respect to T when the volume is constant. So we need to understand the physical meaning of this. And the left side of the above equation describe an experimental quantity. Here this is actually the experimental quantity, and it is the small amount of heat transferred due to small difference in temperature between the system and surrounding during a process in which volume of the system is held constant. So this is actually the something experimentally which we can measure, that is the amount of heat, the infinitesimal amount of heat that is transferred from the system to surrounding when there is an infinitesimal difference of temperature between the system and surrounding. Keep in mind, in this case we need to keep the temperature constant. Here if we see the right side of the equation is the derivative of internal energy. Here this is the right side of the equation, so it is the derivative of internal energy with respect to temperature when the volume is kept constant. So by definition we can put that change in internal energy with respect to temperature when the volume is constant, that is the specific heat at constant volume. So we need to put this value over there. So actually the above equation relate experimental quantity on left side to partial derivative of thermodynamic coordinate on the right side. So this is something we need to know, that how the experimental and the partial derivative, experimental quantity and the partial derivative of something we need to relate with each other. If we consider the pressure is equal to constant, that is actually the next part of the last equation, that is actually in this equation. Here in this equation, if we keep the pressure is equal to constant, so what will be the consequence of this? If we keep the pressure is equal to constant, so what we can get from this equation, we can get here that a change in dq divided by dt at constant pressure is equal to change in internal energy with respect to time and volume is constant, plus change in internal energy with respect to volume and temperature is constant, plus P into change in volume with respect to temperature when P is constant. So we can see that by definition that dq divided by dt, that is equal to specific heat at constant pressure, and del V divided by del T at constant pressure is equal to V beta. So in the above, so we need to put this value in the above equation. So we can get that Cp is equal to Cv and plus change in internal energy with respect to volume when the temperature is constant, plus P into V beta. So this is actually some relationship a relationship that is making a connection between the specific heat at constant volume to a specific heat at constant pressure, and the derivative of that particular internal energy. So we can modify the same equation and simplify it to a new form, that is the change in internal energy with respect to volume and temperature is constant, that is equal to Cp minus Cv divided by V beta minus P. So this is something about. So the other thing is we need to know the quasi-static flow of heat, that is actually the heat reservoir. How we can explain the quasi-static flow of heat in the case of heat reservoir? Actually there is some experimental thing we need to know, and from that we can discuss this topic. If we consider there is a finite difference of temperature between a system and surrounding, so what happen? There is a general conclusion that if there is a difference between two objects, a difference of temperature between two objects. So what will happen, due to the difference of temperature, and both the bodies are in thermal contact with each other, so the heat will flow from the object at high temperature toward the object at lower temperature, and this flow of heat will continue until both the body achieve the same temperature. This is for the general case and for very for very general case. But here we can consider some special case where we use the concept of heat reservoir. That is a big reservoir where small change in temperature is unable to make a appreciable change in temperature. So we can go through these slides and then finally give some example relevant to that how it is not able to change its temperature. Of course it changes temperature but not appreciable, so that we cannot measure it because its magnitude is very low compared to the size of that particular heat reservoir. So if we consider some finite difference of temperature between a system and its surroundings, so what happen? So non-equilibrium temperature distribution in the system will occur because there is difference between the system and surrounding, and that will lead to the temperatures, the heat flow between the two objects, and the temperature between the system and surrounding is small, so there will be very slow heat transfer between the objects. So the flow of heat is infinitesimally slow and could be calculated from thermodynamic coordinate. So what happened? Say a finite amount of heat transfer, both the objects are in thermal contact with each other. That is important for us. Two conditions are important for us for important for the heat flow. One is that there should be difference of temperature, and the other condition is that both the objects should be in thermal contact with each other. So a finite amount of heat transfer will not cause an appreciable temperature change in the surrounding. If there is a finite amount of heat transfer, so it will not cause an appreciable temperature change in the surrounding. How we can justify it? Say for example, we have some example of it. If we place an ice cube in the ocean, so ocean is really very big and the ice cube is very very small compared to the ocean, so definitely there is temperature difference between the water of ocean and the ice cube. Huge difference. But when we place the same cube in the ocean, it will not change the temperature of the ocean because ocean is really a very big heat reservoir. Of course it can it will, some energy will be added from the ocean toward the ice cube and that will mix with it, but the change in temperature is ignorable. We cannot calculate it because the size of the ocean is really very big and we can ignore it. Similarly, if we have a small flame, so it will not affect the temperature of the atmosphere. So that is also one of the example of the heat reservoir. So the ocean and atmospheres are the example of heat reservoir. So here we can see that heat reservoir is a body of such large mass so that it can absorb or reject an unlimited quantity of heat without experiencing any appreciable change in temperature or any other thermodynamic coordinate. So we can write this equation that for a particular quasi-static process of a system in contact with heat reservoir, the quasi-static heat flow is given by Cp is equal to dq divided by dt when the pressure is constant. So if we consider the quasi-static isobaric process, so we need to keep the volume constant. So a path integration is given as a Qp is equal to integration, definite integral from Ti to Tf Cp dt, and we can when the Cp is remain practically constant, so what happen, we can integrate, we can keep out the term Cp out of this integration, so we can integrate the term dt. So the equation will be modified as a Qp is equal to Cp Tf minus Ti into Qp is equal to Cp into Tf minus Ti. So this is something for the isobaric process. If we can consider isochoric process where we can keep the volume of the system remain constant, so what happen, the Qv will be equal to change integration from Ti to Tf Cv dt, and similar consideration hold for other system during kinetic process. So this is something for the isochoric process, where we consider this temperature of this volume of the system remain constant, so we can get the equation as a QV is equal to change in the integration from di to df cv dt. That is actually for isochoric process. So this is some discussion about the specific heat, the calorie and the heat reservoir, and for some particular system. So we will have new some other topic in the next lecture. So for now, thank you very much for today's lecture.